Swayam Prabha. Digital India. Educated India.
As an important observation about centroids, let us now take an area which is made up of 2 or 3 simple plane areas, let us say a square, a triangle and semicircular planar area. So, there is one kind of area, here is another kind of area and here is the third kind of area, but all of them are joined together. Then it is very simple to prove that if I want to calculate the centroid of this whole system, then x c of the entire system would be equal to the area of system 1 times its centroid plus area of the second area x c 2 plus and so on divided by the total area and so on. That means, in this case, if I consider the square to be area 1, then x c 1 is known. Similarly, if I take semicircle to be area 2, then x c 2 is also known because we already calculated it, and x c 3 for the triangle is also known. I also know the formula for 3 shapes and therefore can easily calculate the centroid for the entire system. Similarly, y c for the total area is going to be a 1 times y c 1 plus a 2 times y c 2 plus so on divided by a 1 plus a 2 plus a 3 and so on. This comes in handy when we know several areas that are joined together and I know the formula for different areas, but wish to calculate the centroid for the joint area. Let us do a couple of examples using this. I leave the simple proof of this for you to do. So, as the first example, I take a square and join on it 2 triangles, equilateral triangles, one here and one here. I wish to calculate the centroid of this assembly. Let me call this number 1, let me call the triangle here number 2 and let me call the red triangle number 3. Then I know that x c 1, that is the x coordinate of the centroid of the square, is going to be, if this side is a, is going to be a divided by 2. Similarly, the height of this triangle, because the side is a, is going to be a root 3 by 2, and therefore x c 2 is going to be equal to a plus the distance of the centroid from the base, which is nothing but 1/3 the height, and therefore a divided by 2 root 3. And x c 3, that is the x coordinate of the centroid of the third triangle, is going to be right on the dividing axis, and which is going to be a by 2 again. And therefore, x c of the entire assembly is going to be equal to area of the first square, which is a square times a by 2, plus area of the second one, which is going to be equal to the base, which is a, times the height, which is a root 3 by 2 divided by 2, that is the area, times XC2, which is A plus A divided by 2 root 3, plus the area of the third one, which is A by 2 A root 3 divided by 2 times A by 2 divided by the total area, which is A square plus A by 2 times A root 3 by 2 plus A by 2 times A root 3 by 2. That is the formula for XC. And you calculate this comes out to be about 0.594 times A. By symmetry, YC would also come out to be the same, and therefore, for this assembly where I have a square of side A, a triangle, equilateral triangle on top and on the side, this is A, X, Y, I get XC to be, which is summation AI XCI, I am writing a general formula, divided by summation AI, which is comes out to be 0.594 A, slightly to the right of the centroid of the square, which is expected because of the area added onto the right, it shifts to the right, and similarly you can calculate YC is going to be come out to be again 0.594 A. So, this is how you use this observation, that if I want to calculate the centroid for an assembly of plane areas for which I know individually where the centroid is going to be, I can calculate the centroid for the total assembly. Let me take another example where I have an area formed by taking away a semicircular area from a square of side A. So, I wish to calculate the centroid of the shaded area, where the shaded area has been formed by taking away a semicircular area from a square of side A. Again, I can use the same theorem, but in a different way, because now what I am going to say is that X C of the square, which I already know is going to be right in the middle, is going to be equal to X centroid of the shaded area plus X centroid of the semicircle. This is area of this square, area of this square is going to be equal to XC of the shaded area times area of the shaded area times the area of the semicircle. So, area of the square times the centroid of the square is going to be equal to area of the shaded area times the centroid of the shaded area plus X C centroid of the semicircular area times the area of the semicircle, and therefore, X C of the shaded area is going to be equal to A square times X C of the square minus X C of the semicircle times area of the semicircle divided by the area of the shaded portion, which is going to be area of the square minus area of the semicircle. And that is what we wish to calculate. We have already calculated that for a square, X C is going to be A by 2, where A is its side. The radius of the semicircle is equal to A divided by 2, and I know from the base we already calculated this, the centroid is at a distance of 4r divided by 3 pi, and therefore xc with respect to this origin of the semicircle is going to be equal to a minus 4 over 3 pi times a by 2, which is a minus 2a by 3 pi. This is the xc of the semicircle. So now we are all set. I know xc for the square, I know xc for the semicircle, and area of both, area of square is equal to a square, area of semicircle is equal to pi by 2 times a by 2 whole square, and therefore I can calculate the xc for this shaded region from the formula that we derived earlier, and xc comes out to be, you plug in the numbers, 0.314a. Notice that if I had removed an entire, this half, let me make it with blue, if I had removed this half blue of the square, the xc would have been here at 0.25 a, but because of this extra area which I am showing here to the right, the centroid shifts slightly to the right and is at 0.314 a, which is greater than 0.25 a. That would have been the case if I had removed this entire half of the circle. Y coordinate, obviously because of the symmetry, remains at a by 2. So I have given you two examples of how to use the observation that the centroid of a given area is actually a weighted combination of centroids of the areas making this joint area to calculate centroids of complicated shapes.